So we had a very productive collaboration, so we shared the office for maybe a decade or two at UC Berkeley, which is the coffee shop that is downstairs. And so Roland had his, I believe it's a bachelor degree in Tübingen, Germany, in 1987. And then Colorado Boulder, he had his MS and a PhD at Stanford University in 1993. His research interests are very broad: tectonics and rheology, seismology, geophysics, you name it, it's there. And I think I understood the earthquake cycle is his main, or one of his great interests. And so it will be the topic of our seminar today. I have a list of awards here that's huge. And so is a fellow of the American Association for the Advancement of Science, and a fellow of the American Geophysical Union, and then a bunch of other things that really describe how great it is to have him here with us. The format, the hybrid format, it's the first time we have it. We don't have too many people here, but I think it's good. It's a good start. You are the first one that experienced, a seminar at INGB. And we are very honored to have you here. And the seminar today is Subduction, Megathrust, Coupling, and Slip through Earthquake Cycle. Roland.
Thank you, Luca. And yes, we did share an office in a coffee shop where I'm every morning, and he was every morning too. And this was a place for lots of productive work and discussions. So I want to thank Luca, Michelle, and Salvatore for inviting me to INGV. I want to thank Chris for inviting me to the FEAR Tectonic Seminar series, virtual series. And I thank both for agreeing to have it both happen here today in hybrid form to sort of, things are turning towards better conditions. And so it's great to be here in person, to visit here during my sabbatical in Europe. As Chris indicated, and I confirmed, it's fine to ask questions during the presentation, both in the room and otherwise, and I hope the hybrid format will work well. And given the hybrid format, we did have some technical challenges. I also want to thank the technical staff and Irene and Elisa for helping troubleshoot that. I think now it's working great. So subduction zones and deformation of subduction zones, it's a really complex system that involves the megathrust and off-fault viscoelastic deformation at depth, etc. And there's a lot to be learned about the mechanisms and the hazard associated with subduction zones. And today I thought I would focus on just the part of the deformation of this very dynamic system that relates to slip, the distribution of slip in space and time on the megathrust. So interseismically, the distribution of coupling, earthquake cycle deformation in terms of co-seismic, post-seismic slip. And then we have seen over the last few years increasingly evidence for changes in slip rate, transient slip events, and changes in coupling. And so I'll give you a number of examples from work that we have done that relate to all those topics. And this is work with a large number of collaborators, students, former students, postdocs, whose papers I list here. So I'm going to work my way through these 4 different topics, and I hope you will agree that they link to each other in the common theme of how dynamic and complex and interesting the behavior of the megathrust is. That goes well beyond what we thought maybe when I started out my career as a young assistant professor, was the nature of earthquake cycle deformation of the subduction thrust. And I guess in the end, there's still sort of the sense we've come quite far in this type of research, but there's still a lot to be learned, both observationally. So this is partly also a pitch for more observations, especially closer to the source and offshore seafloor geodesy and seismology, as well as the need for more physical mechanical modeling of these systems. As these observations gel and improve, we have the opportunity to learn more about what these observations mean from advanced modeling, where the modeling here is probably still quite simplistic and doesn't really get yet at the full spectrum of underlying processes. So megathrust coupling, so the distribution of slip rate and slip deficit rate on the megathrust is a really important measure of the mechanical state and the hazard of a subduction thrust. And it's a very important first order thing. We want to know where's the fault currently slipping aseismically and therefore has less of a slip deficit rate, and where's it fully locked and therefore capable of rupturing in a large earthquake, so increased earthquake potential. Now, what you see here are two realizations of a coupling model. So red areas are areas of high coupling, constrained by the same data, and the only thing that's different about them is the additional regularization of the inversion of on-land GPS data. The model on the left is one where a Gaussian smooth shape of the arc-normal distribution of slip was assumed. So slip decays, coupling decays back to low values, both at the trench and down dip. And the model on the right says, we favor models that have high coupling at the trench and then decays away from that. And they're hugely different, right? There's an order of magnitude different moment deficit contained in these, and the deformation data don't know the difference. So we really have very little ability to constrain coupling from on-land geodetic data. So this was Cascadia in the Pacific Northwest, the Western US. And this is a model of coupling of Northeast Japan, so offshore Honshu, that Loveless and Mead developed in a paper that was published just a year before the Tohoku earthquake. And so here again, they used a smoothing approach that decayed the coupling to low values away from a peak coupling zone in the middle. And that fell ultimately proved to be a wrong way to regularize your model, because the Tohoku earthquake ended up having its peak slip of 40, 50 meters or so right at the trench. So the coupling, the slip potential, the earthquake potential was underestimated by this model. And so this is from a figure that Jack and Brendan published right after the earthquake, where they essentially said, look, we realized that we used a regularization in our earlier paper that was proven problematic based on the lesson of the earthquake. So they didn't just sort of let it go, but they emphasized that contract. And that's, again, due to the geodetic data alone in a kinematic inversion. If we just optimize how much coupling we have in different places, what the slip deficit distribution is, we just have no resolution at all in those areas that are blue on this right panel. And this is a last example from Chetka, from an earlier paper, where the only thing that is different between these 5 different models shown here is the smoothing parameter, essentially how much smoothing is being applied in the kinematic inversion from the on-land GPS data. And you can see, depending on the smoothing parameter, the distribution, the heterogeneity, and the amplitude of coupling differs greatly. But the misfit in the data, the weighted residual sum of squares values, don't really vary that much. So you might say, well, that's not good. So let's just give up on this whole trying to meaningfully constrain coupling from geodetic data alone. However, what we also emphasized in that earlier paper is when you do a kinematic inversion, you're not really considering if the model that you invert for, that coupling distribution, is also mechanically, physically very realistic. So what you see in the top left panel here is a model where rather than kinematically inverting for slip, we're loading the subduction thrust by plate convergence and slip down dip of the zone that you see colored in the surface projection here. And then we fully couple, we fully lock. We say that white band is frictionally locked, is not able to slip until the next earthquake. And then we solve for what is the slip rate allowed for by this physical model. And you can see up dip of the locked zone, even if you let that shallow part of the fault slip as much as it wants to, as much as the stress can drive it. So there's no friction in here. It's just however much shear stress you put in that, or shear stress rate, that's as fast as will slip. You can see if you have this shattering, if you have this pinning of the system by a locked section in between, the shallow part can slip any faster than maybe 20 millimeters per year or so. And so what that means is if you think you know where the fault is locked, such as based on information of where we had past earthquakes. So on the top right, you see a distribution of the proposed rupture zones of historical earthquakes over many decades prior to the observation period here. And we just say, okay, let's just couple all those. How do we do, right? And you can again see that stress shadow effect up dip of the thick coupled areas. You see very, very low slip rate. Now, this model does a horrible job fitting the data. If you look at the red arrows, you can see that similar to the one in the top left with that wide band of locked zone, we way over predict. You have inland velocities that are much higher than those that are observed, the black arrows with the 95 confidence ellipses. So that makes it appear that the rupture zones are too big to be the fully locked asperities. And so when we reduce the size of these asperities, we simply shrink them. And we have to shrink them to about 25% of what was initially proposed to be the rupture zone based on mainly aftershock distributions. Then we're starting to do a decent job fitting the data. So the lessons from this is that the fully coupled, fully locked portions of the subduction thrust, at least in this case, seem to make up only a small fraction of the presumed rupture zone of great earthquakes. And if true, that would be quite important to know with respect to the mechanical properties of the subduction thrust. So Eric Lindsay, when he was a postdoc at EOS in Singapore, and I co-advised him during that time, he developed an inversion method that takes the stress shadowing effect into consideration. So it assesses both the fit to the data, but also how much slip the system can allow given what the distribution of slip is. So it takes the stress shadowing effect into account. So on the right, you see a simple 2D profile view of how that might work. So if you impose a distribution of slip like the black line shown in the lower right, the synthetic model input, right? You can see there's very slip allowed near the trench, and then there's a section that's completely coupled, and then a gradient to full aseismic slip. In a kinematic inversion informed by on-land data, the little triangles shown on the right, all the models that fill out that orange possible range of slip are equally permitted, because in that near trench area, the model has no resolution power. If you apply the stress shadowing constraint, then only the blue zone is physically plausible. So we're ruling out all the models that can't be, because the stress shadowing, there's just no way for stressing rate to get to these shallow parts of the system. So that's really the whole idea of this method. So whereas, again, going back to Northeast Japan, if we make models where we minimize the coupling, so similar to these Gaussian distributions that we saw earlier, and one that maximizes it, we again have this problem, that whole wide range of possibilities just from the kinematic inversion. If we apply the stress shadow effect, that additional constraint, then we find a model that's looking much more like the one where we maximize the coupling. So the message being, with this very simple, physically very logical additional constraint, we come up with a coupling distribution that is much higher. That's important for hazard, and has these additional constraints. We have a physical constraint that helps us minimize the range of possibilities. Now, there were actually some seafloor geodetic data that were collected in the time prior to the Tohoku earthquake. And if we consider those in the inversion, you can see that in this case, even though there are just 3 of them where we have a velocity, the coupling model doesn't change much. So the constraint model does already a really good job fitting the seafloor geodesy data. So if we just do kinematic inversions, then if we had seafloor GPS acoustic measurements everywhere, we would get closer to the right answer. But even just with this one simple additional constraint, we do better as well. So, and this is, again, simply a matter of where without that physical constraint, we have great uncertainty, essentially no constraint for slip near the trench, as shown on the right panel. Whereas with that added stress shadowing constraint, the uncertainty of the inferred coupling is much, much, much reduced. Okay, so with that in mind, let's move on to Alaska, where just in the last couple of years, we had 2 large earthquakes, a 7.8 in July of 2020, the Semyonov earthquake, and then almost exactly a year later, and just to the northeast, an 8.2 event in 2021, the Chiknik earthquake. And shown on this figure is also in this gray shading, the distribution of coupling inferred from kinematic inversions in multiple studies with a constraint that maximizes coupling near the trench and then allows for gradients away from that, and then allows in a segmented way for gradients, as you can see, to lower coupling, lighter shades of gray towards the west. So the 2 earthquakes apparently occurred in a zone of low coupling. And here's again the latest iteration of that coupling model that was refined with improved GPS data. And you can see that the Semyonov earthquake and its aftershocks lie in a zone that, if we take this as what it is, the earthquake happened in an area where coupling was minimal. And that would sort of break the whole idea of earthquakes happening where the fault is substantially locked. So we applied the approach to our models of the Alaska subduction zone, and this is work by Bin Shao that hopefully will be accepted any day now, similar to what we had done in Kamchatka before. So we couple just the historical rupture zones of great earthquakes that were either inferred from aftershock zones or from inversions of seismic, teleseismic, and or geodetic data. So 1964, one of the greatest earthquakes, etc. That model, just like in Kamchatka, over-predicts the landward, northward motions. So there's too much coupling on the megathrust. The upper plate gets tracked towards the plate interior too much. And so if we play again that exercise of shrinking the locked asperities to about 1/4 of the size, then we're starting to fit the data with a coupling model that looks completely different from the one that came from the inversions alone, and suggest again that the truly frictionally locked core asperities are very, very small. And then the reduction of interseismic slip, so increase of coupling surrounding these, comes purely from the stress shadowing effect, that pinning of the plate interface. Now this model you can see fits better. The reduced chi-square is reduced by a factor of 6 or so. But what this doesn't take into account yet is the two last earthquakes, the Semyonov and TECTONIC earthquake that you maybe barely see there in the middle. So if we again couple the interior of those, then we get an even better fit to the data. In fact, this is the model that truly fits as well as the inversion. That last one wasn't quite there yet. Now, one thing is interesting here in the West, in the zone of low coupling, right here, this is where there was a very large tsunami-producing earthquake that had unusually low frequency. It was a tsunami earthquake, and the rupture zone extent was estimated from seismic data to really be that large ellipse that you see here. And that one we had to shrink to essentially 0 and push the locked part really close to the trench. So in that area, this is part of the so-called Shumagin gap, coupling appears to be, based on the geodetic data, essentially near 0. So this is important. That means that we can have these tsunami earthquakes in zones where, as best as we can tell, there's almost no coupling left, with the limitation of having almost no constraint on that at the trench.
Roland,
Yep.
It's Chris. Would you mind if I just clarify something about this 25% number? Is really interesting. Is it possible that there's more of a checkerboard pattern to it, or does it have to be the geometry that you're showing here?
That is absolutely possible, right? Because here, in a forward modeling sense, we're just shrinking the locked zone, right, sort of symmetrically into the center of the main slip patches. So when you see this sort of small patch for 1964, that's because there were 3 peak slip asperities, so there are 2 more to the northeast. And yes, it could be much more heterogeneous, and that actually may make much more sense. But here we're just sort of doing this forward modeling exercise rather than trying to see if we can pull out more detail. And remember, right, the geodetic data alone don't resolve much detail at all. So I think the key message is that the coupling, the distribution of fully locked zones, the size of these is much smaller than the apparent rupture zones in the earthquakes, as best as we inferred from teleseismic, geodetic, etc. inversions. So that may tell us something about the mechanical properties, right? Truly, fully, persistently locked asperities are quite small, and the surrounding areas may be what we sometimes refer to as conditionally stable or low velocity weakening, low A minus B, able to slip dynamically when pushed really hard by an earthquake.
Thank you.
Okay, so then we had the recent pair of earthquakes. The Semyonov earthquake, it's pretty well constrained by geodetic and seismic data. There are a number of papers with inversions of those, and they all agree in that the slip, the zone of co-seismic slip, is pretty much limited below 20 or even 30 kilometers. So it occurs kind of between 20 and 40 kilometer depth, with no evidence of co-seismic slip updip from that. So the key question is, does that mean the updip portion is still has slip deficit and is a potential source of future destructive earthquakes, and especially tsunami-producing earthquakes? Or is it uncoupled and it's just catching up by aseismic, post-seismic slip, and slipped already prior to the earthquake, as this model might suggest is happening? And then the TECTONIC earthquake model is from an inversion by the US Geological Survey, mainly from teleseismic data, but also considering GPS offsets. So the occurrence of an earthquake gives us an opportunity to probe the megathrust in more detail, because we're hitting it with a stress increase from the earthquake. We can look at the response of the fault zone to those stress changes. And from that, by modeling that data, hopefully learn something about the mechanical properties of the megathrust away from the coseismic rupture. And so here are two different realizations of an after-slip kinematic inversion. So you can see the post-seismic slip amounting to as much as a few decimeters is in this inversion found to sort of be overlapping with the coseismic rupture. Is obviously the spatial resolution is very poor, seems to have a low slip zone near the peak slip of the earthquake and a little bit more slip towards the southwest compared to the northeast. Again, you can see how many GPS stations there are, or how few, I should say. The details of this are not very well constrained. So similar to how we made our model just a little bit more physical by considering the stressing rate on the subduction thrust that is related to the stress shadowing effect from locked sections, we can model afterslip using a very simple first order realization of rate and state friction velocity strengthening response, sort of saying, well, we might not understand all the underlying processes, but from many studies we have found that afterslip can be quite well represented by the relationships of the state of stress on the fault, the stress change, and a frictional response that relates to, in this case, just a steady state implementation of the rate and state expression as proposed by Silva and Barbeau. So now we're parameterizing our model fault by imposing a coseismic rupture. We're surrounding it wherever we think that's appropriate with a velocity strengthening rheology following this relation. And then we can compare that with our deformation data. And now the only parameters we're changing is the initial velocity V naught and the A sigma parameter, the rate state parameter times the effective normal stress. And we don't know those independently unless we know independently what the effective normal stress is from other information. And so the realization of the model that fits best is shown here on the right. So here we're allowing afterslip to occur everywhere surrounding the coseismic rupture. So we're saying this earthquake is in fact embedded in an otherwise slow slipping velocity strengthening, wants to slip aseismically, and when you push it with an earthquake or every year endoseismically, it'll just creep. And on the left is shown by testing through the parameter space, the values of the rate state parameters. So really just two values. If we look at models where we say, well, let's only allow the fault to respond in this velocity strengthening way down dip of the rupture, because we think that's where the fault is hard. We know it's aseismic for sure. We don't fit the data well at all. Similarly, if we only allow afterslip up dip of the rupture, but not down dip, we don't fit the data well. So you can see that the weighted residual sum of squares get up by a factor of 2 or more if we do that, shown by the text down there. So that means, based on this model, this confirms that the up dip zone, at least in an area as wide as where we see that afterslip, and actually wider, because you wouldn't get that much slip due to the stress shadowing effect if there were locked fault up dip from there, seems to be fully velocity strengthening. And this model predicts not only the spatial distribution of displacements measured with GPS, but also the time dependence, the decay as shown in these time series from the nearby GPS stations. If we also look at the temporal distribution of aftershocks, cumulative number of aftershocks as a function of time in the first 3 months after the earthquake, they seem to also have the very comparable, very similar time dependence. And that has been argued by some to mean that these aftershocks directly reflect the slip on the fault. So these are on-fault aftershocks that may ultimately witness or highlight, illuminate the temporal decay. But there's some debate about that always being the case. Now on the right, you can see there are a lot more aftershocks, these magenta dots to the west of the rupture than they are to the east. And when we look at the difference in inferred slip from the kinematic inversion and the stress-driven model on the right, there is more slip in the kinematic inversion to the west towards that zone of aftershocks. And the aftershocks, in fact, lie outside of the area where we would expect to see coseismic stress accelerating slip on the fault. So we think, without having very tight constraints on that, that may be a zone, that zone where we have these more distant aftershocks is actually a zone where the slip that occurred post-seismically is not simply relieving the stress added by the coseismic rupture, but had already built up some slip deficit. So there's essentially a triggered slow slip event above and beyond afterslip driven by the coseismic stress. And I think it's important to distinguish that. Not all slip after an earthquake is afterslip in the sense of purely relieving the stress added by the coseismic rupture by velocity strengthening response, which is all a velocity strengthening fault can do, but can also in some cases be a slow slip event that was triggered by the earthquake and may have released that additional moment that we see indicated in the kinematic inversion further to the west. And this is the afterslip model for the TECTONIC earthquake. This is just a preliminary result that's been put together soon after the earthquake. In this case, he found that making the A-B parameters up dip and down dip of the rupture, up dip and down dip of 25 kilometers different, seemed to improve the resolution. So there's some ability, the better the data get, of actually mapping out the distribution of frictional parameters if we can constrain the time-dependent, space-time dependent slip response in the aftermath of the earthquake. And so I'll show just two examples of ongoing studies that sort of, with that idea that the better our data get, we really want to make our models more physical and informative about the underlying processes. I think this nicely shows that. So this is a dynamic rupture model that Du Li, who's a postdoc working with Alice Gabriel at LMU in Munich, where I'm currently visiting, where the model is informed by the pre-earthquake coupling using the published coupling distribution prior to the work that we did here, and then optimizing a coseismic dynamic rupture model, also taking into consideration the effect of pressurization, thermal pressurization of the fault, coming up with a simulation that produces a slip similar to that inferred from kinematic inversion and a moment rate distribution as a function of time that also compares well to seismic data. So rather than just solving for the kinematics of the earthquake, trying to get information about the pre-earthquake stress distribution and the distribution of frictional properties. And then a second example that I find very exciting and is something that I think we can hopefully go towards for this recent pair of events. This is a study by Primus et al. And this is on a strike slip earthquake, the Napa earthquake, just a little bit north of where I live. And this is a model, it's an inversion for the distribution of rate state frictional parameters on the fault and conditions on the fault, pre-stress, A and B, and all those things that is optimized to satisfy both the information about the co-seismic rupture, so seismic waveforms and geodetic data, and the post-seismic deformation in the first month or so following the earthquake. And then by running many thousands, tens of thousands of models, optimizing that parameter space, so that what we're modeling, what we're trying to infer, is the spatial distribution of frictional properties on the fault, right? So this comes much closer to what we hope to do in the laboratory when it comes to inferring what is the distribution of mechanical properties on a fault that make an earthquake be what it is, and the post-seismic slip response. So I think this is a cool result. So in summary for this, it looks like only the core asperities of what we think from various pieces of evidence was the size, the extent of a co-seismic rupture are truly fully 100% locked. The surrounding areas seem to slip at a lower rate, but they're not fully coupled. Otherwise, our interseismic models would, we would have models that don't fit the data, over predict the apparent coupling. There are some zones on the megathrust. There's this 1946 zone right here, where we see little evidence of any coupling. So zones that produce tsunami earthquakes may have relatively modest kinematic coupling. And so only if we put offshore instrumentation there might we be able to capture that. The frictional afterslip, by looking at the post-seismic deformation, helps us illuminate the rheological properties surrounding the recent two earthquake. And we still have limitations of resolving coupling in the shallow part. So that's where we need additional observations. And just to point out, the 1938 earthquake, that was a very large 8.3 to 8.5 earthquake. Since then, we already accumulated a slip deficit of 5 meters. So in the aftermath of the 2020-2021 earthquake, I wouldn't be too surprised if there could be ultimately more happening there, because there is already quite a large slip deficit in that area. Okay, so we'll stay in Alaska and move maybe 1,000 kilometers to the northeast to the Cook Inlet, where a couple of studies, or actually a number of studies, have shown the occurrence of slow slip events that are very enduring. These are multi-year. There was one in the Upper Cook Inlet that lasted for 5 years, from 2009 to 2014, and a 2-year-long event in the Lower Cook Inlet. These are down dip of the rupture zone of the 1964 earthquake. In the area of Upper Cook Inlet, you can see right here in these light ellipses, this is a zone that also produces tectonic tremor, similar to what we see in Southwest Japan and Cascadia, and is usually interpreted as being a direct reflection of a seismic slip. So we have these enduring multi-year slow slip events occurring near, maybe up dip somewhat of this tremor producing zone, where the tremor only occurs in this northeast portion, in a zone where apparently there's a thicker lithosphere being subducted, this so-called Yakutat plaque, that seems to delimit that zone of tremor. So Baptiste Rousset, who was a postdoc with me in Berkeley, is now at CNRS in Strasbourg. We visited this Upper Cook Inlet 5-year episode. So he first did a kinematic inversion of the spatial distribution of slip, shown here on the left. You can see one of the GPS sites, a north component time series, showing nicely the enduring transient that lasted about 5 years. Now, in the bottom right is the tremor catalog that Aaron Reck from the USGS determined. And you can see, yes, there's tremor during that multi-year long-term slow slip event, but there's tremor at other times too. And during the slow slip event, the tremor only occurs in short bursts, right? It's not happening at all the time. Now, if you look at the zone here highlighted in green, where that bar, where one of the bigger tremor bursts happens, maybe you can see on the GPS time series, there's a little bit of an acceleration. There's a little bit of a kink. So if we zoom in on that, you can see that in the top right here, there is in fact, over the course of about a month, the GPS station has an accelerated southward motion. And at the same time, the tremor space-time distribution, when the colors indicate time, flew at the beginning of September through the end, has a space-time progression to it. So there seems to be contained in that enduring long-term 5-year slip event, a shorter pulse of slip and tremor in just a 2-week period or so, as indicated by the GPS data. So now, given how little this event is, this was a magnitude 6.9 equivalent in the inversion, as opposed to 7.6 of the 5-year slip event. Batiste went ahead and did a time-dependent slip inversion. So solving for the distribution of slip, not just in space, but also in time, using a so-called network inversion filter. That's kind of a Kalman smoothed version where the smoothing is applied both in space and time. And what you can see based on this, slip started without any tremor at the beginning of the month in the first few days, started to propagate towards the southwest along the 40-kilometer contour line or so. Then tremor starts at about 11 days and then nicely follows the slip. And then tremor kind of fizzles out where the slips may be continuing for another week or so. Because obviously the smoothing might spread out that signal. And so this is constrained by just a few millimeters of displacement through time by the GPS data. So it seems like that this is contained in that 5-year event. There's this little burst in acceleration. So we can look at that more systematically. We essentially add up, we look at cumulative displacement, cumulative southward displacement of the GPS side during times when there's tremor, indicated by these bars on the left, and compare that with the cumulative displacement as a function of times during times of no tremor. And so on the right here, you can see if we just keep adding the displacement whenever there's tremor, and we do the same thing whenever there's not tremor, the apparent slip, the slope of that line of cumulative slip, is substantially higher, several-fold higher during times of tremors. So there wasn't just one acceleration in that 2-week-long period in September, but every time when there's tremor, there is also more displacement and presumably more slip. So we have a 5-year slow slip event that actually is made up of many, many little guys that ultimately produce the total slip right here. Now, remember, the tremor didn't stop after the long-term slow slip event, but in the catalog that Aaron Weck produced, there continued to be tremor bursts later. So if we go through the same exercise and look at displacement during times of no tremor in blue, they actually go backwards to the north, indicating we see kind of a coupled situation. And during the times of tremor, again in red, the stations move again towards the south. So both during the 5-year slow slip event and afterwards, when there was slip, it occurred during the times of tremor. So the combination of the tremor and the GPS data kind of illuminate this much more complicated episodic accommodation of slip in this area. Now we know that interseismically, so or inter-slow slip event, long-term slow slip event, it looks like there are these smaller bursts of magnitude 6 and bigger slip events that occur episodically. Now, during that 5-year episode of acceleration, we actually can't be sure if the scenario in the lower left, B, is right. We just slip more per little event for 5 years and then slow down. Or if there is a zone of fully aseismic long-term 5-year slow slip that gets added to the episodic pattern. So the geodetic data that are still limited in their spatial distribution, as you can see here with the triangles, just doesn't have the resolution power to give us that information. Okay, so now coming to the fourth case study, we're going to Cascadia. So in Cascadia, somewhat similar to that eastern part of the Alaska subduction zone and similar to Southwest Japan, we have a shallow locked part of the subduction zone. If we apply Eric Lindsay's stress shadow informed coupling model, we find a model that's more similar to the model that was maximizing coupling shown to the right. And quite far away from that, separated by what is indicated as a transition zone on that left panel, there is a zone of tremor that occurs very episodically. And so this is where episodic tremor and slip was born, where Herb Traeger and colleagues around the same time as Abara-san in Japan discovered that slow slip and tremor indicate transient time-dependent slow slip events that propagate reliably up and down the subduction zone. Separated in between by this, what is called the transition zone, where it looks like the fault is just kind of slipping aseismically steadily, or so we thought. Here's a time series of a GPS station. It's detrended after removing any annual seasonal cycle from hydrological loading. And so you see, and this is a station that's right above the tremor zone right here. And you can see how we have displacement jerking back towards the west, etc. This is exactly the signal that we have come to expect where we have ETSs. We're here every 10 to 12 months or so, the fault suddenly accelerates in the tremor zone, produces westward motions, and then it locks up again, and it starts accumulating strain again. So we know this already quite well, because this has been studied now over many, many, many slow slip cycles that recur quite reliably and quite regularly. Now here's the time series of a station further west, so closer to shore right here, and that looks different. So we don't see the ETSs so well anymore because we're further to the west. So this is the zone where we always thought this is in that transition zone, and for some reason the fault has a rheology that makes it slip steadily all the time as has been captured with GPS so far. But what you see instead is, right, you can see there's sort of linear piecewise sections that we label T1, T2, T3, T4 that clearly have a different east velocity, somewhat more a higher velocity, a higher east velocity, so more towards shore or less towards shore. Now this is just one station. Now what's interesting is that changes in velocity seems to coincide with the times of magnitude 6.5 and up earthquakes, strike slip earthquakes that occur in the Gorda oceanic plate offshore. That is a zone of quite distributed brittle faulting of the plate. So the Gorda plate is being squeezed by the Pacific plate, pushing the Gorda plate and the triple junction up to the north. So what's happening due to these earthquakes that makes the velocity of that station change towards more landward and less landward. So it's not just that station that's doing it. Now here in the middle panel, panel B, you see the change in velocity between period T2 and T3, separated by the 6.8 earthquake, shown here in green. You can see that this cluster of sites here in the center has an increased landward velocity, right? And if you do the same kind of differencing, so change in velocity between T3 and T4, where we had a 6.6 earthquake, a little bit further offshore, we see just the opposite pattern. So the one on the left looks like there's a bit more coupling, more dragging towards the east, and the one on the right, just the opposite. So we can invert the data for change in slip rate on the megathrust that can explain the change in surface velocities as indicated by the GPS rate differences. And what we see is here in blue, there's this zone of increased coupling, so less interseismic slip, lower interseismic slip rate, just up dip of the Tremont slip zone in that transition zone that we previously thought is only slipping steadily. And then if we take the T3 to T4 change in velocities, you get higher slip, acceleration of slip, in exactly the same patch where previously we saw an acceleration. So we have a change in coupling due to the occurrence of an earthquake, where in one case, the earthquake increased the coupling, made the plate interface more stuck, and the other case, a decrease in coupling. So that's really strange, right? What could happen? We looked at the static stress changes. They're minimal. These 6.5 earthquakes offshore produce very little Coulomb stress change on the megathrust, and usually in a sense that doesn't even really nicely encourage or discourage down dip slip. So this must be a dynamic effect. There's shaking that's quite strong, and the strong ground motion from all these offshore events are quite substantial and quite comparable. So here's the idea that we ultimately put forward to explain this. The thing that really differentiates the two cases, the one separated by the earthquake in 2014 versus the one in 2016, is in the first period, we just had a really big Tremont slip episode, right? We're just at the very end of the ETS. The second event happened at a time when there was very little tremor. There was a little burst right here, but nothing else happening. So in what way could be time since the last down dip ETS affecting how a fault, how the megathrust in the transition zone responds to this offshore earthquake? And so the conceptual model that we put forward is that in the first case, we just had a slow slip event down dip in ETS. So there was slip, there was dilatancy, fluid pressures dropped due to the dilatancy. So we had a zone of decreased fluid pressure down dip of the transition zone. Then the earthquake happened offshore, shook up the system, and opened up cracks, a valve, opened up permeability, increased permeability in the fault zone. And because we just decreased pressure down dip, fluid flow would be expected towards that low pressure zone, thereby decreasing the effective normal stress, increasing the effective normal stress, decreasing the fluid pressure in the transition zone, and therefore clamping up the fault, reducing the slip rate. In turn, in the other case, we're deep in the ETS cycle. There hasn't been slip in the ETS zone in a long time. Fluid pressure is at the peak. Now we're opening up the fault zone, the valve, and we have a pressure gradient the other way. So we then increase fluid pressure in the transition zone, decreasing the effective normal stress, allowing for slow slip. Now that's a conceptual model that requires, some physical modeling to see if this works. And I'm really interested in alternative ideas that we might come up with to otherwise explain what's happening. But right now, this is still our preferred interpretation of this dynamically triggered both increase and decrease in coupling associated with shaking from earthquakes just offshore. And, valving is happening. I put in this slide in the last minute. These are pictures I took on a field trip with Whitney Bear and Amanda Thomas's groups on Sears Island. And we looked at all the geology, and we talked geophysics about low frequency earthquakes and tremor and slow slip.
Roland,
And in this zone, yep.
Roland, it's Chris. I don't know if you can see Joan Gomberger has her hand up. Joan.
I do not see that, but please, yeah, go ahead, Joan.
Please.
Yeah, so there are earthquakes of that size and roughly those distances are quite common in the Gorda Plate. And many of them appear to not do anything to change the slip rate at all. How does that fit the events that don't seem to have any effect?
Yeah,
Your model?
That's a great question. So during the period we consider here, right, we had 4 events, and for that earlier change from T1 to T2, there would still be a consistent decrease in coupling. In 2005, we don't have pre-event data. There was just another event, as you know, just last December, and we don't yet have enough GPS data to see if that pair of events with an event on the Mendocino fault zone together with an event in the Gorda Plate again changed the coupling. It's a really important question. I know that Noel Bartlow at SSA presented a poster that I haven't seen yet, but it was all about following up on your question, looking at other times when there were earthquakes and seeing if this apparent change in coupling in this zone here in the south also happens at the time of other events outside of this area, and also do we see similar things in other areas. So it's a really important thing to see, is this ubiquitous, we just haven't looked yet, or is there something unique to this particular area and or time period that we currently span with our GPS data?
Okay, thanks.
Yeah, so it's a really good question. I know Noel is eager to pursue this more, and hopefully others will too. So back to my pretty serious pictures, right? So this is nominally in the zone of, in the deep zone. This is Plucius, eclogite facies, rocks near a megathrust, and we see these huge veins, decimeter wide, that in some cases, based on the mineralization in there, may have opened up in very sudden events. And so this is kind of what I'm envisioning maybe is happening when I talk about we're opening the valve and we're fluids just gushing through the tremor and up-dip transition zone, right? So in the geologic context, there's ultimately what's really happening. This is kind of how I'm envisioning this maybe looking like. So to sum up this final case study, the coupling in the transition zone is not just uniform slow slipping at a steady rate, but at least in this one example, we see changes in slip rate. And those changes seem to coincide with the time of so far the 3 largest nearby earthquakes during a 10 or 12-year time period. And so this does indicate that there may be this dynamic effect that these earthquakes induce on the fault zone. And because we see both increases and decreases in coupling for 2 events that in terms of the shaking they produced is very similar, we think it has something to do with this valving process and maybe with the time in the ETS cycle that we put forward in this very conceptual model. So as I said at the very beginning, we need more observations. So SC40, an initiative in the US that is currently in the planning and community building phase, is hoping to eventually get the resources in collaboration also with the USGS and various sponsors to build an observational system, a combination of on-land and offshore geodetic and seismologic observations of different types. So this is sort of a notional schematic illustration of what we envision would really change our ability to resolve these things in situ with near-field observations. And then couple that with more physical models. So there's a separate but collaborative effort, the Modeling Collaboratory for Subduction Zone Science, the MCS group, that aims to develop the models of subduction zone processes, including those related to slip on the plate interface, that would then benefit from the observational improved constraints to develop increased understanding of what's really happening mechanically, and thereby hopefully also help understand the system and the associated hazards in much more detail. So I hope that was interesting, and I hope you have lots of critical questions that we can discuss for as long as those questions keep coming. So thanks very much, everybody in the room and everybody on Zoom.
Fabulous. I'll ask everyone online to unmute long enough to join me in thanking.